name is Professor Orata. Good afternoon or good morning, depending on where you are. Today we look at temperature entropy diagram. Just remember that if you're dealing with a reversible process, like involving heat engines, then there's heat absorbed or heat applied in the system and then heat discarded or rejected in the system. And so going back to our Clausius inequality dq over T as related to the change in entropy, we know that dq then is related to entropy in that manner there. So that if we integrate this quantity here, then we have that dq will be T ds. And if we call the process the path with which we supply heat, some path A to B, then the heat supplied QAB will be given by the integral A to B T ds. And the heat rejected, because it's a reversible process, the heat rejected is basically Q. That's heat supplied. Heat rejected will be Q. BA is equals to integral of BA T ds. That's heat rejected or discarded. And of course, being a cyclic reversible process, we know that from first law of thermodynamics, remember, for processes, du is equals to dq plus d minus dw for work done by the system. We said the plus or minus there is just a notation. It doesn't bear much significance whether it stands for work done by the system or work done on the system. And so we are saying for a cyclic process, remember, if the process is cyclic reversible cyclic process, du is 0. And so dq is equals to dw, or q is equals to w. So the heat supplied is the same as the work, and so forth. Now, if we go to the temperature entropy diagram, we have the saturation curves forming the dome shape. So that's saturated liquid, remember? And that is the saturated vapor. And that's the critical state. Here we have the superheat region, the subcooled region. And so we have, where we have the wet vapor, in this region we have liquid, saturated liquid coexisting in equilibrium with saturated vapor. Very important for us to note. Now, what is the enthalpy, the entropy change in this system under constant pressure? Suppose we are starting at some state point, let's call it alpha, and you increase the temperature of the liquid. At this particular point, beta, the temperature will be relatively constant up to the point gamma. And then when you hit the saturated vapor curve, then the profile will be that. Let's say, let's put some state point there. Let's call that alpha, beta, gamma, sigma. And in this particular region, the wet region, we are seeing that the temperature is constant at that point, and this is a constant pressure line. That's a constant pressure line. This constant pressure, remember? Pressure is constant. So, from the Clausius inequality, ds is greater or equal to dq over T, and a constant pressure that becomes dH over T. or the change in entropy when we move from phase beta to gamma will therefore be the integral of dH over T. But remember that T corresponds to the saturation temperature, which we can label here as TB, T beta. So that this will be delta H gamma beta over T beta. This delta H there is the latent heat for that process. Very simple. Just working on Clausius inequality. And we are saying that we take this liquid, raise the temperature at that state point, we'll start having formation of saturated vapor, formation of vapor at that particular point. Of course, the temperature is constant during such phase transformations. And of course, when we read the saturated curve, now we are in the superheat region. We're in the superheat region, which are marked with the state point sigma. Now, in the superheat region, we remember that for constant pressure, we have said ds greater or equal to dqp T, which we have said is dH over T. But what is dH? dH is the isobaric heat capacity times the change in temperature. Remember, Cp is equals to dH over dt. So if we plug in that, we will have Cp dt over T. And so in the superheat region, the change in entropy, in the superheat region, the change in entropy will be ds is equals to Cp dt over T, and then we integrate. So we will have delta S. Delta S will be Cp natural log of some change gamma, where Cp now will be the isobaric heat capacity of the superheated vapor. Now we don't focus much the liquid region because there's very little effect of pressure, the effect of pressure on the change in entropy. Just think of it or remember it from our earlier discussions that we said for water, the pressure temperature diagram for water, solid, liquid, gas. We said that at this point corresponding to the triple point where the pressure was 0.006112 bars and the temperature is 0.0098 degrees centigrade, we said that this point, which is the triple point, where solid, liquid, and gas coexist in equilibrium, and of course the variance of that system or the number of degrees of freedom at that point is 0. This point here is fixed. And at that point, we say that at the triple point, we say that the entropy is 0 and the internal energy is 0. So there's very little change in the subcooled region there when you're working with this system here. So we are not focusing much on it. Now, in terms of specific volume, profile. Volume profile. You will find that the specific volume profile is almost like that of constant pressure. It's almost like that of constant pressure. That is V. It's almost like that of constant pressure. Not forgetting that we had gotten expressions for specific volume. We say that if we have X of vapor, 1 minus X of liquid, then X of vapor plus Vf minus X, specific volume of the liquid. If we factorize out, we have F plus X, Vg minus Vf. Remember G, vapor, F, liquid. And we said that since Vg is much greater than that of liquid, then V will be X of G, or X is equals to V over Vg. Remember, these are values you can get this for these properties. Specific volume, if we take it at this point here, you can get from the steam table the specific volume, the liquid, specific volume, the gas. Depending on temperature, we can get those values from the steam table and actually compute our values for the volumes, because we know we can get those values from the steam table. So if you look at the lectures on tabulation of properties, then we have discussed at length some of these quantities in the steam table. Now, the other thing which you need to be interested in is the dryness fraction, which measures the quality of the wet vapor. The dryness fraction X, which measures the quality of the vapor. And how we go about doing that? So we have our temperature and we have our entropy. Temperature and entropy, that's S. Dome shape, saturation curves. And so what are we saying? At different temperatures, we remember we said on the saturated liquid curve, X is 0. And on the saturated vapor curve, X is equals to 1. Remember that. Because what is the dryness fraction? Is mass of dry steam divided by the sum of the mass of dry steam and that of the liquid. And so if we take the values at different temperatures and mark those points, then we will find the line of constant dryness, where that will correspond 0.25, 0.50, and 0.75. Then of course we have for the 1. Right? That's the line of constant dryness. Because dryness fraction, very important first note. In summary, very simple. The key question there for handling the entropy temperature diagram is the Clausius-Clapeyron equation, and realizing that heat transferred under constant pressure is the change in enthalpy, heat transferred under constant volume is the change in internal energy, and that relationship between thermodynamic state function and chemical observable is fundamental in all these works, in all these thermodynamic calculations. Very, very important. And then we now know, based on those expressions, we're able to get the latent heat, we are able to get the change in entropy in the various regions of the temperature entropy program. Of course, that's the superheat region. It's always so good to remember that that's that, and the subcooled region. Very important for us to take note of that. And we are able to generate also the specific volume curves, the constant pressure lines. We are able also to generate the line of constant dryness, that is the X values, constant X values at different temperatures. And so very important for us to know how to deal with these temperature entropy systems. Let's stop at that particular point, and thank you very much.